Now let's go over all of the algorithms you will need for this course. These can be categorized into search algorithms and sort algorithms. We'll cover search algorithms first. The linear search is one way to search a data structure like an array. This algorithm searches through an input array for a value. To do this, the code starts at index 0 in the array and compares the item in the array to the search value. If there is no match, the code moves on to the next index and repeats this until the item is found, in which case it returns the index that it found the item in, or until the entire array is exhausted without finding the item, in which case it returns -1. And if we try to run this program over here, we get the value 6, and we can verify this by just looking at the array. So this is index 0, 1, 2, 3, 4, 5, 6, and this is the value that we searched, so we know that this linear search is working properly. Key advantages of linear search include that it's simple to implement and it works on an unsorted array. Its time complexity is O(n), and its space complexity is O(1), as the possible amount of iterations depends on the size of the array, and it only ever defines one variable, I. The other searching algorithm is binary search. Binary search only works on sorted arrays. How it works is it finds the middle value, compares the target value to the middle value, and then rules out the half that must not contain the target. This process repeats for smaller subarrays until the target value is narrowed down. For example, in this example input, say we want to find the value 66. We first retrieve the middle value, which is 31. Since 66 is bigger than 31, we can now rule out 31 and this entire left side of the array. So we can just put a little crossover. And now let's focus on the smaller array over here. In this smaller array, the middle value is now 60. Since 66 is still bigger than 60, we can now rule out 60 and this left side of the array as well. And now we're down to this small array over here. In this smaller array, 66 is smaller than 74, so we rule out 74 and then we eliminate the right side of the array, so all of this. And now the middle value here is just only one value, it's 66. Thus, we found our target value in only 3 iterations, as opposed to if we used linear search, it would have taken us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 iterations. Here is a function that performs binary search on an input array R, searching for an input. We first define variables low and high to point to the array's first and last element. Then, we define middle as the middle element by taking the mean of the low and high pointers. We then compare our target value to the array's middle value, and we update the low and high pointers accordingly, which essentially narrows down the array. Here's a visual diagram for what's going on. You can see that the low, mid, and high variables point to their array elements. The code low equals mid plus 1 that we just saw essentially puts our low pointer right here, which essentially eliminates this half of the array, as the pointers low and high are now limiting the array to this little subsection over here. And inversely, the code high equals mid minus 1 puts the high pointer right here, limiting the array to this little section right here. And then after that, we calculate the mid again, so we put the mid over here. And then again, if the variable that we're looking for is greater than, then we put low over here. And if it's less than, then we put high over here. And this continues until the mid variable is the value we're searching. So if the middle value is ever our target, we return the middle index as the index we searched for over here. We want this to loop while the array still has unexplored areas, meaning when our low variable is less than or equal to our high variable, because our low variable being in a higher array position than our high variable wouldn't make sense. If this condition isn't true, that means the entire array has been exhausted without finding our target, meaning that the search was unsuccessful, so we return a -1. This algorithm has a time complexity of O log n and a space complexity of O of 1. If we try to run this program, we get 7, and we can verify this by counting in the array. So we have 0, 1, 2, 3, 4, 5, 6, 7, and that is the exact index that we searched for in this call.